The universe was once completely dark and empty. Then a profound transformation began. This pivotal moment is called the cosmic dawn, the mysterious era when the first stars, galaxies, and black holes ignited, burning away the cosmic dark ages. By the end of this journey, you will know the 25 greatest puzzles that define our cosmic origins. We will investigate how supermassive black holes appeared out of nowhere and why the very first stars have vanished without a trace. What single cosmic mystery do you find the most compelling? Our very first mystery takes us to the birth of the stars themselves, but these were not the familiar suns dotting our night sky today. We call them population 3 stars, and they were cosmic titans of a kind we can scarcely comprehend. Born from the pristine, raw ingredients of the newborn universe, they were composed of nothing but hydrogen and helium, the 2 simplest elements. This pure, uncomplicated fuel burned with a ferocious intensity, forging stars that could be hundreds, even 1,000 times more massive than our own sun. Imagine a single star so brilliant it could outshine an entire galaxy of modern stars. But such power came at a great cost. These stellar giants lived fast and died young, burning through their nuclear fuel in only a few million years before exploding in spectacular, seed-scattering supernova. Their entire life cycle was a fleeting cosmic flash, so brief that not a single one of these firstborn stars remains in the observable universe today. This is the core of the mystery. They have vanished, leaving no direct trace for our telescopes to find. So how can we possibly prove they ever existed? Astronomers search for their ghostly chemical fingerprints. When those first stars exploded, they scattered the very first heavy elements, carbon, oxygen, iron, across the cosmos, polluting the next generation of stars. We now hunt for the most ancient, long-lived stars we can find, analyzing their atmospheres for that pristine, telltale signature of material forged only in a population 3 supernova. Finding that faint chemical echo would be like discovering the fossil of the very first creature to walk the Earth. It would confirm our deepest theories about the cosmic dawn and reveal the nature of the engines that built the very universe we call home. Those stellar explosions did more than just forge new elements. They began to change the very fabric of space. After the first stars and galaxies ignited, the universe was still shrouded in a thick cosmic fog. This was not a fog of water vapor, but a pervasive sea of neutral hydrogen gas, blocking light from traveling freely across the vast distances of space. Then a monumental event unfolded, one we call reionization. Over hundreds of millions of years, an intense, invisible radiation swept through the cosmos, stripping electrons away from all those hydrogen atoms and transforming the fog into a transparent, ionized plasma. The universe, for the first time, became clear. We live in that clear universe today, but we are left with a profound question. What were the lights that burned away the fog? What were the primary sources of this ionizing radiation? The suspects are few, but each is a titan of the cosmic dawn. The leading candidate has always been the first generations of massive stars. Their furious ultraviolet light could have been the primary tool for cosmic cleaning. Yet, some scientists argue that the first galaxies, packed with billions of such stars, were the true engines of reionization. Their collective power would have been immense, and then there is a third, more exotic possibility. What if the primary sources were not stars at all, but the voracious supermassive black holes at the centers of those early galaxies, blazing as quasars and flooding the cosmos with even more powerful radiation? This is not just an academic debate. Identifying the dominant source is key to understanding how our structured universe came to be. The James Webb Space Telescope is now our greatest tool in this investigation. It peers back in time, hunting for the faint, earliest glimmers of starlight and the telltale signatures of ancient black holes. Its mission is to count these first light sources, to measure their brightness, and finally determine which of these cosmic behemoths was responsible for clearing the cosmic air, allowing the light of countless future galaxies to shine through. This cosmic clearing set the stage for an even more profound mystery. How did the universe's first supermassive black holes, some with billions of times the Sun's mass, appear so astonishingly fast? We find them blazing as quasars when the universe was less than 1 billion years old, a mere blink in cosmic time. Growing such monsters from scratch so quickly is like asking a newborn baby to suddenly become the heavyweight champion of the world. The sheer speed of their formation defies our basic understanding, pointing to a cosmic shortcut we have yet to discover. Two main theories compete to solve this puzzle, and both face immense challenges. The first idea suggests that vast, pristine clouds of primordial gas, undisturbed by stars or galaxies, could have collapsed under their own immense gravity. In this scenario, they did not form a star at all, but bypassed that step entirely, crumpling directly into a massive black hole seed. This would give them a huge head start, a seed thousands of times more massive than anything a star could leave behind. The competing theory argues for a more traditional, yet equally extreme path. It posits that the first generation of colossal stars, the population 3 giants, lived their short, violent lives and then collapsed. The remnants of these stellar titans would have been the first stellar mass black holes, tiny seeds in comparison. The problem is the clock. How could such a small seed, perhaps only 100 times the mass of our Sun, gorge on enough surrounding matter to balloon into a billion solar mass behemoth in less than 1 billion years? The feeding process should have been messy and inefficient, generating intense radiation that would push material away and slow growth to a crawl. Neither theory perfectly explains the evidence we see. The direct collapse model requires very specific, pristine conditions that may have been rare. The stellar seed model seems too slow to account for the giants we observe. This leaves us with a fundamental gap in our knowledge. Did we miss a crucial ingredient in the early cosmos? Was there some exotic form of matter that accelerated their growth? Or does our understanding of black hole physics itself need a radical rewrite? The race is on to find the smallest, most ancient black holes with new telescopes, hoping their size will reveal which cosmic path they truly took. The sheer speed of black hole growth is not the only puzzle from that era. It forces us to confront an even deeper and more pervasive cosmic mystery, one that involves a substance we cannot see or touch. The very first stars and galaxies could not have formed without the invisible scaffolding of dark matter. Think of it as a hidden gravitational glue, an unseen foundation upon which the luminous universe was built. In the early cosmos, ordinary matter, the stuff that makes up stars, planets, and us, was spread too thin. Its gravity alone was far too weak to pull together the first structures against the universe's rapid expansion. But dark matter, which outweighs normal matter by a factor of 5 to 1, provided the necessary gravitational pull. It collapsed first into vast web-like structures, and normal matter, primarily hydrogen gas, simply flowed into its gravitational wells. Only then, within these concentrated pools of dark matter, did gas have the density to cool, condense, and finally ignite into the first stars. So we know dark matter was the essential architect, but what exactly is it? This is one of the most profound questions in all of physics. The leading idea suggests it is cold dark matter. This means its particles move sluggishly, allowing it to clump together easily from the very beginning, creating a hierarchy of structure: small clumps first, then larger galaxies. This model does a remarkably good job of explaining the large-scale cosmic web we observe today. However, some observations of the smallest, faintest galaxies pose a challenge. They seem less numerous than cold dark matter predicts, as if the formation of the tiniest structures was somehow suppressed. This has led to an alternative proposal: warm dark matter. In this scenario, the particles would be much lighter and faster, streaming freely across the young universe and effectively smoothing out the smallest gravitational bumps. This would delay the formation of the very first and smallest galaxies, potentially solving the missing satellite problem. The type of dark matter is not an abstract detail. If it was warm, the cosmic dawn would have started later and progressed differently, with a distinct pattern of the very first lights flickering on across the cosmos. Our ability to understand the birth of the first galaxies is therefore inextricably linked to deciphering the true nature of this invisible cosmic architect. Without knowing its fundamental properties, our picture of the universe's first chapters remains frustratingly incomplete. This cosmic scaffolding of dark matter left behind a ghostly imprint, a fossil record written not in stone but in light. When astronomers point their most powerful telescopes at the brilliant, distant beacons known as quasars, they see something astonishing. The quasar's intense light does not travel to us in a clean, uninterrupted beam. Instead, it passes through a vast, cosmic labyrinth of invisible hydrogen gas clouds that filled the early universe. Each cloud acts like a filter, absorbing a very specific fingerprint of light known as the Lyman alpha line. The result is a spectacular pattern etched into the quasar's spectrum. Instead of a smooth rainbow of colors, we see a dense, dark forest of thousands upon thousands of absorption lines, each one representing a different cloud of hydrogen at a different distance. This is the Lyman alpha forest, and it is one of our most valuable windows into the cosmic dawn. It is not a collection of trees, but a complex barcode of the universe's adolescence. Each line in this forest is a direct snapshot of a patch of neutral hydrogen gas as it existed billions of years ago. By reading this barcode, we can map the large-scale structure of the young cosmos, tracing the vast, web-like filaments of matter and the immense voids that separated them. The great mystery lies in decoding this cosmic diary. The patterns in the forest change dramatically depending on the era. Before reionization, the universe was thick with neutral hydrogen, and the forest is dense and tangled. As reionization progresses and the ultraviolet light from the first stars and galaxies burns away the fog, the forest begins to thin out. Patches of the universe become transparent, and the absorption lines start to disappear. By studying the exact density and distribution of the lines in quasars at different distances, we can pinpoint precisely when and how this great clearing happened. But the data is incredibly complex. It is like trying to listen to a single instrument in a symphony of thousands. We have the diary of the universe's formative years open in front of us, but it is written in a code we have not yet fully cracked. Unlocking it would tell us not only the timeline of reionization, but also reveal the precise nature of the very first structures that ever lit up the cosmic dark. These ghostly forests of hydrogen lead us to an even more startling discovery. The James Webb Space Telescope has ripped up our cosmic playbook, revealing a universe that grew up far faster than we ever thought possible. The crisis began when Webb peered back to the very edge of the observable universe, to a time when the cosmos was a mere 5% of its current age. There, in the ancient darkness, it found galaxies, not the faint, infant smudges scientists expected, but brilliant, massive, and fully formed cosmic cities. These galaxies are impossibly bright, filled with mature stars, and appear to have evolved at a speed that defies every simulation we have. It is like opening a history book to the first chapter and finding a photograph of a sprawling, modern metropolis where there should only be a few scattered villages. This is a direct challenge to our most fundamental models of galaxy formation. How could so much structure assemble so quickly after the Big Bang? The gravity of dark matter alone, as we currently understand it, seems to work too slowly to explain such rapid growth. This has thrown cosmology into a state of profound reevaluation, forcing us to consider radical new ideas. One possibility is that star formation in the early universe was wildly more efficient than it is today. Perhaps in those pristine clouds of pure hydrogen and helium, with no heavier elements to help the gas cool and fragment. Stars formed in enormous single bursts, creating brilliant stellar factories almost instantly. Another, more exotic solution points to the dark matter itself. What if dark matter is not completely cold and sluggish? What if it has some unique property, a slight warmth or an ability to interact with itself, that allowed it to clump together faster and seed galaxies sooner than our models allow? Or perhaps we are witnessing the effects of entirely new physics, a primordial turbulence in the universe that gave structure a powerful head start. Each of these potential answers carries immense implications. If star formation was that efficient, it would rewrite the life story of every galaxy. If dark matter needs revision, we are fundamentally reimagining the invisible skeleton of the cosmos. Webb's stunning images are not just pictures of ancient light. They are a direct challenge, a message from the dawn of time telling us that our universe is even more mysterious and wondrous than we dreamed. This challenge of missing galaxies strikes close to home, right in our own cosmic backyard. Our most sophisticated simulations of the universe paint a very specific picture of a galactic neighborhood. They show that a giant galaxy like our Milky Way should be surrounded by a bustling swarm of thousands of smaller dwarf galaxies, the leftover building blocks from the cosmic dawn. These ancient relics are the surviving fossils of the first small structures to ever form. Yet when we look up, we find only a few dozen. The vast majority are simply not there. This is the missing satellite problem, and it represents a fundamental mismatch between our theoretical expectations and our observational reality. So where did all the little galaxies go? One compelling solution suggests they are not actually missing. They are right where they should be, but they have gone dark. In this scenario, the smallest clumps of dark matter did indeed form, just as the simulations predict. They captured their share of hydrogen gas, but their gravitational pull was so weak that the gas could not condense and collapse to form stars. Perhaps a nearby supernova explosion in one of the few active dwarf galaxies blew all the star-forming gas out of these tiny halos, or maybe the intense ultraviolet background radiation after reionization heated the gas, preventing it from ever cooling down. The result would be a vast population of dark matter ghosts, invisible halos devoid of stars, orbiting our galaxy completely unseen. Another, more violent possibility is that many of these small satellites were indeed born with stars, but they were torn apart by the immense tidal forces of the Milky Way long ago, their stars scattered into our galaxy's halo. We may be living in the aftermath of a cosmic demolition, surrounded by the faint stellar streams of digested galaxies. This mystery forces us to question the very nature of dark matter. Could it be that our assumptions about it are slightly off? If dark matter were a bit warmer, its particles would move faster, preventing it from clumping into the very smallest structures. This would naturally lead to fewer dwarf galaxies, neatly solving the problem. The search for these missing satellites is therefore a direct probe into the conditions of the early universe. Finding a way to detect the proposed dark matter ghosts or confirming their absence will tell us if our galaxy's quiet neighborhood is the result of astrophysical processes we understand, or a sign that we need to rewrite the rules for the cosmos' invisible architect. This sequence of events is a cosmic chicken and egg puzzle of the highest order. What truly ignited first in the darkness? Did a single, monstrous star blaze into life alone? Or did the collective pull of a dark matter halo forge an entire proto-galaxy that then lit its first stellar fires? The order of operations holds the key to understanding the entire genesis of structure. We desperately want a simple timeline, a neat chain of cause and effect, but the cosmic dawn resists such simplicity. The formation of the first stars, the assembly of the first galaxies, and the ignition of the first supermassive black holes may not have been separate, orderly events. They could have been a chaotic, overlapping cascade, with each one influencing the others in a fierce feedback loop. a massive star could form and explode in a stellar heartbeat, its shock waves triggering new star formation nearby while its black hole remnant begins to feed, all within the same swirling primordial gas cloud. Trying to separate these births is like trying to pinpoint the exact moment a thunderstorm begins amidst the first drops of rain, the first flash of lightning, and the first clap of thunder. They are all part of the same explosive system. Our challenge in constructing a timeline is immense. The light from that era has been stretched by the expanding universe into the far infrared part of the spectrum, becoming incredibly faint. It is a whisper from the edge of time. Astronomers act as cosmic detectives, using different tools to listen for different parts of this whisper. The James Webb Space Telescope is designed to catch the direct starlight from the earliest galaxies. Meanwhile, giant radio telescope arrays scan the skies for a different signal, the faint radio hum emitted by the neutral hydrogen gas itself, a background hum that was silenced as reionization progressed. By combining these views, along with sophisticated computer simulations that model the physics of the early universe, we try to reverse engineer the sequence. The simulations are our testing grounds, allowing us to play out different scenarios. What if stars formed first? What if black holes were the primary actors? We then compare the results of these digital universes to the real, observational data we are now collecting. The current best guess suggests that the first stars, the lonely population 3 giants, likely flickered on first in small, dark matter halos. But they were probably quickly followed by, or even coexisted with, the first tiny, irregular galaxies. The black holes are the wild card. Did their seeds form before, during, or after the first major waves of star formation? The answer is still written in that faint, redshifted light, a narrative we are only just beginning to read. This timeline of creation is written in the faintest light, but there is another, even more fundamental message from the beginning. It is written not in photons, but in the very fabric of space-time. We are hunting for the echoes of the Big Bang itself, ripples known as primordial gravitational waves. These are not the waves from colliding black holes that we detect today. These are the tremors from the universe's violent birth, a relic from a period of hyper-expansion called inflation, which occurred in the first trillionth of a second. Think of the cosmos as a vast, silent lake. The Big Bang was the cataclysm that sent a monumental wave crashing across its surface. Inflation was that initial, unimaginably fast surge, and the primordial gravitational waves are the faint, ever-expanding ripples that remain, carrying a perfect imprint of that first explosive moment. These ripples would have subtly shaped everything that came after, including the distribution of matter that eventually led to the first stars and galaxies. The great hope is that these ancient ripples left a unique fingerprint on the oldest light we can see, the cosmic microwave background. As these gravitational waves moved through the hot, dense plasma of the early universe, they would have subtly polarized the light, creating a distinct swirling pattern, a specific type of curl known as a B-mode pattern. Finding this pattern is the ultimate goal, a direct snapshot of the universe at its very inception. The challenge is that this signal is incredibly weak, buried under a sea of other polarizations from interstellar dust and other astrophysical sources. It is like trying to hear a single, faint whisper in a stadium roaring with noise. Experiments like the BICEP array at the South Pole and future space observatories are designed to listen for this whisper. Detecting it would be one of the most profound discoveries in the history of science. It would confirm the theory of cosmic inflation and tell us what powered that explosive growth. More than that, it would open a window into an era before the cosmic dawn, a time when the very laws of physics as we know them were being forged. It would reveal the initial conditions that set the entire cosmic story in motion, telling us why our universe has the structure, the stars, and the galaxies we see today. These primordial ripples set the stage for another invisible force that sculpted the cosmos. Woven through every galaxy and the vast voids between them are cosmic magnetic fields. Their origin is one of the great unsolved puzzles of the cosmic dawn. Were these magnetic threads part of the universe's initial blueprint, created in the first frantic moments after the Big Bang? Or were they forged later, spun into existence by the first swirling disks of gas around newborn stars and the violent outflows from supernova? The evidence points to a fascinating middle path. The seeds of magnetism were likely incredibly weak, perhaps imprinted on the universe during its epoch of inflation. These faint seeds were not the powerful fields we detect today. They needed an amplifier. That amplifier was motion. As the first structures formed, gas began to swirl and move. In a process similar to a bicycle dynamo, this turbulent motion could have stretched and twisted those weak primordial fields, dramatically strengthening them over millions of years. This dynamo effect, operating within the first protogalaxies, may have been the engine that built the magnetic cosmos we live in. But why does this matter for the story of the first stars? Magnetic fields are not just cosmic decoration. They play a crucial role in how gas behaves. They can provide support against gravity, slowing the collapse of a gas cloud. They can channel material, directing flows onto growing stars and black holes. Most importantly, they are essential for launching powerful jets and outflows from these first cosmic engines. These outflows, in turn, enrich the cosmos with heavy elements and regulated star formation. Without magnetic fields, the early universe might have been a much more chaotic and inefficient place. The great challenge is that these initial fields are nearly impossible to observe directly. Their signal is incredibly faint, buried in the polarized light from ancient galaxies and the subtle effects they have on cosmic rays. Decoding their origin is like trying to find the source of a single note in a symphony that has been playing for 13 billion years. Yet, if we can trace these magnetic threads back to their beginning, we will understand a fundamental force that guided the cooling, collapse, and ultimate ignition of the very first structures in the dark. These magnetic fields guided the raw material for the universe's most critical transformation. For millions of years, the cosmos was a place of profound chemical simplicity, containing only the three lightest elements, hydrogen, helium, and a tiny trace of lithium. Everything that makes up our world, the carbon in our bodies, the oxygen we breathe, the iron in our blood, was utterly absent. The birth of the first heavy elements was a cosmic alchemy that forged the very ingredients for planets and life from this primordial soup. The central mystery is identifying the primary forges where this elemental creation occurred. Which cosmic cataclysms were responsible for building the periodic table from scratch? The first and most obvious suspects are the supernova of the population 3 stars. When these colossal giants reached the end of their brief lives, they exploded with unimaginable force. In their fiery hearts, nuclear fusion forged heavier elements, and the supernova blast itself created even more under extreme pressure and temperature. These stellar explosions would have scattered newly minted carbon, oxygen, and iron across the cosmos, seeding the surrounding gas clouds. But were they the only cooks in the kitchen? A second, more exotic possibility involves the violent collisions of neutron stars. When these incredibly dense stellar corpses spiral into each other and merge, they are thought to be factories for the universe's heaviest elements like gold and platinum. Could these mergers have been common enough in the early universe to contribute significantly to the first waves of enrichment? A third candidate is the most energetic explosion of all, gamma-ray bursts. These brilliant flashes, potentially linked to the deaths of the very first stars, could have ejected newly forged elements at near light speed, spraying them far and wide. So how do we distinguish which event was the primary source? We become cosmic archaeologists. Instead of digging in the earth, astronomers point their telescopes at the most ancient stars still shining in our galaxy, stars that formed from the polluted gas left behind by those first supernova and mergers. These ancient suns are living fossils. By analyzing the precise cocktail of elements in their atmospheres, we can read the recipe of their birth cloud. Finding a star enriched with large amounts of oxygen and magnesium, for example, points to the signature of a core collapse supernova from a massive star. If we find an ancient star surprisingly rich in gold and europium, that might be the telltale sign of a neutron-star merger that polluted its nursery. The search is for these chemical fingerprints, the specific patterns that act as a cosmic crime scene report, pointing back to the explosions that created them. Each ancient star we analyze is a time capsule holding the elemental truth of the cosmic dawn, revealing which titanic events built the world from nothing. This puzzle of missing dwarfs has a powerful and even more baffling cousin. We call it the too big to fail problem. It confronts a strange and specific contradiction between our theoretical universe and the one we actually observe. Our most advanced computer models tell us that the largest and most massive dark matter clumps that formed during the cosmic dawn should have possessed an incredibly strong gravitational pull. They were the cosmic heavyweights, the halos that were simply too big and too powerful to fail at the task of galaxy formation. Their gravity should have easily drawn in vast amounts of gas, compressed it, and ignited brilliant dwarf galaxies that would still shine brightly today. Yet when we search the skies around our own Milky Way and our neighboring galaxy Andromeda, we find a profound emptiness. These massive, predicted halos are not there. Or more accurately, the luminous galaxies they should host are missing. It is as if we predicted a bustling metropolis based on every known law of urban development, but when we arrive, we find only a dark, empty field. So what cosmic force could have prevented these gravitational giants from succeeding? The leading theory points to a form of cosmic sabotage that occurred during the era of reionization. Picture the universe as it was just beginning to light up. The first stars and galaxies were not just beacons, they were powerful engines of radiation, flooding the cosmos with an intense, energetic ultraviolet light. This universal background radiation acted like a persistent cosmic heat lamp. Now, imagine one of those massive dark matter halos trying to form its first stars. It gathers a large reservoir of hydrogen gas, but before that gas can cool down, condense, and collapse into stars, the pervasive ultraviolet radiation from all the other early galaxies constantly heats it up. The gas is kept too hot and energetic to settle down. It is like trying to form ice cubes in an oven. The halo's gravity is strong, but it is fighting a universal environmental force that keeps its fuel from cooling and igniting. This process, known as photoevaporation or radiative feedback, may have permanently sterilized these massive halos, leaving them as dark, starless ghosts. Another possibility is that supernova explosions from the first, feeble bursts of star formation within these halos blew the remaining gas out completely, shutting down any future growth. The result is the same, a population of massive, dark matter structures that are completely invisible to our optical telescopes, their immense gravitational potential locked away in darkness. Solving this mystery is critical because it tells us about the delicate balance between gravity and radiation in the infant universe. It reveals that the first lights did not just illuminate the cosmos, they also cast long shadows, actively shaping which structures would succeed and which would be doomed to eternal darkness. The darkness did not lift like a single curtain falling. The end of the cosmic dark ages was a slow, messy dawn, a drawn-out struggle between light and shadow. We often picture a moment when a universal switch was flipped, bathing the cosmos in light, but the evidence tells a far more intriguing story. Reionization was a patchy and complex process, a cosmic battle fought over hundreds of millions of years. So what was the final blow that ended the darkness? Did a single, brilliant quasar achieve what billions of stars could not, burning a permanent hole in the fog? Or was it a coordinated, universal outbreak of star formation, a final, brilliant wave of galactic ignition that flooded the last remaining pockets of neutral hydrogen. The clues we have point away from a simple, singular event. The light from the cosmic microwave background carries a subtle imprint of this era. As the CMB photons traveled for billions of years, a small fraction of them scattered off the very first free electrons created during reionization. This scattering left a faint, telltale polarization in the light, a ghostly signature of the clearing. By measuring this polarization, we can estimate when, on average, this process occurred. But this gives us a global average, a blurred timeline that hides the local details. It tells us the war was mostly over by the time the universe was around 1 billion years old, but not how the final battles were won. For that, we look to the distant quasars. Their light acts as a probe, illuminating a single, narrow line through the ancient cosmos. When we analyze the Lyman alpha forest from quasars at slightly different distances, we see a stunning variation. Some lines of sight show a forest that is still incredibly dense and tangled, meaning that along that path the fog was still thick. Other sight lines, looking back to the exact same cosmic time, show a forest that has already thinned dramatically with large transparent gaps. This is the smoking gun. It means the universe did not reionize uniformly. It was a cosmic patchwork of ionized bubbles growing and merging over time. There were brilliant islands of clarity in a sea of darkness, and it took eons for those islands to finally connect and conquer the last vestiges of the neutral fog. This patchiness makes pinpointing the precise end, the very last neutral hydrogen cloud to be evaporated, incredibly difficult. The conclusion of the Dark Ages was not a moment, but a drawn-out process whose final gasp remains one of the most active and elusive quests in modern cosmology. This small-scale crisis within dwarf galaxies strikes at the heart of our cosmic models. When we simulate the universe using the standard cold dark matter recipe, we expect these tiny galaxies to possess a very specific internal structure. Their dark matter halos should be incredibly dense at the very center, forming what scientists call a cusp. Imagine a mountain with an impossibly steep, sharp peak, where gravity grows overwhelmingly strong as you approach the summit. That is the cuspy profile our best theories predict. Yet, when we observe the actual motions of stars within many real dwarf galaxies, we find something entirely different. The centers are not steep peaks, but gentle, rounded hills. The dark matter seems to be distributed in a much shallower chord profile, as if some force has repeatedly scooped out the dense center, leaving a gravitational pothole. This is not a minor discrepancy. It is a direct challenge to the cold dark matter paradigm on the very scales where it should be most dominant. If dark matter is truly cold and non-interacting, moving slowly and feeling only gravity's pull, then nothing should stop it from piling up into those dense central cusps. Its presence is felt only through its gravity, so the existence of these cores implies that something is counteracting that pull. What force could possibly smooth out the invisible foundation of a galaxy? One compelling solution is that dark matter is not completely non-interacting. Perhaps dark matter particles can occasionally bounce off each other, a property known as self-interacting dark matter. Think of it like a crowded room. If people are completely unaware of each other, they can all pack tightly into the center. But if they occasionally nudge or push one another, that constant, gentle repulsion will naturally spread everyone out, preventing a dense crowd from forming in the middle and creating a more even distribution. Over billions of years, these tiny, cumulative interactions could have transferred energy from the outskirts of the halo into the center, effectively heating it up and smoothing the sharp cusp into a soft core. Another, more dramatic possibility involves the power of ordinary matter. Intense bursts of star formation in the early life of a dwarf galaxy would have produced waves of supernova explosions. These cosmic bombs could have violently sloshed the gas back and forth within the dark matter halo. This rhythmic churning, like shaking a bowl of marbles, could have transferred enough energy to the dark matter itself, gravitationally pushing it outward and carving out a core. The implications for the cosmic dawn are profound. If dark matter self-interacts, it would not only solve the cusp core problem, but also alter the formation of the very first structures. Those self-interactions would suppress the formation of the smallest, densest dark matter clumps, potentially explaining why we see fewer ultra-faint dwarf galaxies than predicted. The nature of dark matter on this tiny scale dictated the population of the first stellar systems to emerge from the darkness. Was the cosmic dawn illuminated by a few brilliant giants or a myriad of faint, tiny sparks? The answer depends entirely on what we discover about the hidden conversations happening in the dark. These stellar cataclysms were far more than just spectacular finales. The death of a population 3-star was a fundamental force of creation and destruction, an event so violent it could dictate the future of the cosmos around it. The most massive of these giants are thought to have died in a particular kind of explosion known as a pair instability supernova. This is not the same as the supernova we see today. In a normal supernova, the core of the star collapses into a neutron star or a black hole. But in a pair instability event, the core becomes so incredibly hot that the radiation inside it spontaneously transforms into pairs of electrons and their antimatter counterparts, positrons. This transformation robs the core of its outward pressure, causing it to catastrophically implode under its own immense weight. The resulting thermonuclear explosion is of a scale we can barely comprehend. The entire star is utterly obliterated, not even a black hole remains. It is a complete stellar suicide, and the energy released is staggering, outshining entire galaxies and scattering every single atom forged in its core across interstellar space. This is how the universe received its first substantial doses of oxygen, carbon, and silicon, the raw materials for future planets and life, but the mystery lies in what happened next. How did these titanic blasts influence their cosmic neighborhoods? Did they act as midwives or executioners for the next generation of stars? The answer is likely both, and it depended entirely on the environment. In one scenario, the expanding shockwave from the supernova could have acted like a cosmic snowplow, slamming into nearby clouds of pristine hydrogen and helium. The immense pressure could have compressed these clouds, triggering gravitational collapse and sparking the birth of a new cluster of stars. In this way, a single stellar death could have given birth to hundreds of new suns, propagating star formation across the early cosmos. But there is a darker, more destructive possibility. The same shockwave that can compress gas can also heat it to extreme temperatures or blast it entirely out of its host dark matter halo. The supernova could have ejected the very fuel needed for future star formation, leaving behind a sterile, evacuated void. Furthermore, the intense flood of ultraviolet radiation from the explosion could have ripped electrons from atoms in distant gas clouds, permanently ionizing them and making it harder for that gas to cool and condense in the future. So which effect dominated? Did these explosions build the cosmic structures we see, or did they tear them down? The legacy of the first supernova is a story of feedback, a cosmic balancing act between constructive and destructive forces. To understand it, we look for the chemical fossils they left behind. The unique elemental signature of a pair instability supernova is imprinted on the atmospheres of the most ancient stars we can find. By discovering these second-generation stars and reading their chemical DNA, we can map the aftermath of those first explosions. Their distribution tells us whether they formed in a region enriched by a single, nearby blast, or if they were born far away from the destructive reach of the supernova's shockwave. The fate of the early universe may have hinged on this violent, elemental feedback, a cycle of stellar death and rebirth that set the rhythm for the cosmic dawn. This relentless search for the oldest starlight defines a modern astronomical quest, the hunt for the highest redshift galaxy. redshift is not a color but a cosmic measure of distance and time. As the universe expands, it stretches the very light traveling through it, shifting its wavelength toward the red end of the spectrum. The greater the redshift, the farther away the galaxy, and the further back in time we are looking. Finding the galaxy with the highest redshift means finding the most distant, and therefore the very first galaxy we can possibly see. It is a race to the edge of the observable universe, a frontier that is constantly being pushed back with each new observation. The techniques used in this search are feats of engineering and patience. Astronomers use deep field surveys where telescopes like Hubble and now James Webb stare at a seemingly empty patch of sky for days, collecting every single photon of light. It is a cosmic fishing expedition in the deepest waters, waiting for the faintest glimmers from the dawn of time to finally arrive. An even more powerful tool is gravitational lensing. This relies on Einstein's prediction that massive objects like galaxy clusters warp the fabric of spacetime around them. This warping acts like a giant cosmic magnifying glass, bending and amplifying the light from galaxies that lie far behind them. A faint, distant galaxy that would be completely invisible to our telescopes can be magnified and brightened by a foreground lensing cluster, bringing it into view. It is nature giving us a free, ultra-powerful telescope. The significance of finding these record-breaking galaxies cannot be overstated. Each one is a time capsule from the universe's infancy, a snapshot of the initial conditions of galaxy formation. When we find a galaxy at a record redshift, we are forced to ask, how did you form so quickly? What does your structure tell us about the dark matter halo you live in? Are you already mature, or are we seeing your very first moments of star formation? The answers reshape our models. A galaxy found at a redshift of 10 tells a different story than one found at a redshift of 15. Each new record holder tests the limits of our simulations and challenges our understanding of how fast the first structures could possibly assemble. The current frontier, as revealed by the James Webb Space Telescope, is already far beyond what we thought possible, with galaxies appearing at redshifts that seemed purely theoretical just a few years ago. This quest is more than a competition for a cosmic trophy. It is a direct journey to the beginning, a mission to find the very first island of stars to ever emerge from the universal dark. These ancient galaxies could not have grown in isolation. They were fed by rivers in the void, a vast and intricate network known as the cosmic web. Picture the universe not as a random scatter of islands, but as a single, interconnected metropolis. Gigantic filaments of dark matter, stretching for millions of light years, form the cosmic highways and city streets. Where these filaments intersect, you find the dense knots that become galaxy clusters. The spaces between them are the immense, empty cosmic voids. This web is the fundamental architecture of our universe, the hidden blueprint upon which everything is built. But the great mystery is how the raw material for star formation, the pristine hydrogen gas, traveled along this cosmic infrastructure. How did it flow from the vast intergalactic reservoirs into the waiting gravitational wells of the first dark matter halos? The leading theory describes a process called cold flow accretion. Imagine a mountain stream fed by melting snow, flowing smoothly and directly into a waiting lake. In this model, the cold, dense gas from the cosmic filament streams along the dark matter highways, channeled efficiently into the proto-galaxies without ever heating up. This would be a steady, efficient fuel line, providing a constant supply of cold gas ready to collapse into stars. It is a gentle, almost peaceful reign of creation. But there is a competing, more violent vision. Perhaps this accretion was not smooth at all. Instead, the gas might have fallen in clumpy, chaotic torrents. Large clouds of hydrogen could have crashed into the growing galaxies, creating turbulent shocks that heated the gas, potentially disrupting star formation before it could even begin. This would be a chaotic and unpredictable delivery system, like boulders tumbling down a riverbed during a flash flood. So which was it, a serene flow or a violent downpour? The answer dictates how quickly and efficiently the first galaxies could have assembled. A smooth, cold flow would allow for rapid, sustained growth. A clumpy, chaotic influx could lead to fits and starts, with bursts of star formation followed by long, quiet periods. The challenge is that this process is incredibly difficult to observe directly. We are trying to see faint, cold hydrogen gas that does not glow with its own light, and it all happened so long ago. Astronomers use sophisticated computer simulations to model these flows, watching digital gas slide along digital filaments. Then they compare these simulations to the faint, real-world signatures they can detect. They look for the subtle absorption lines that this flowing gas imprints on the light of distant quasars, or they search for the faint glow of hydrogen in the deepest infrared images from telescopes like James Webb. Finding the ghostly rivers of the cosmic web would complete our picture of cosmic genesis, revealing the final delivery route that brought the fuel for the first stars from the vast emptiness of space into the brilliant hearts of the earliest galaxies. This cosmic fuel network raises a profound question about the relationship between a galaxy and its dark heart. In the modern universe, a strange and precise rule governs giant galaxies. The mass of the supermassive black hole sitting at the center is almost perfectly proportional to the mass of the galaxy's central bulge of stars. This is not a coincidence. It is a correlation so tight it screams of a deep, fundamental connection, a cosmic symbiosis that has been locked in for billions of years. But did this rule exist from the very beginning? This is a true chicken and egg puzzle from the cosmic dawn. Which came first, the galaxy or the black hole? Did a massive black hole seed form early on, and its immense gravity actively pull in gas to build the galaxy around it, acting as a central anchor for all future growth? Or did the galaxy form first through the collective gravity of its dark matter halo and stars, only later funneling gas to the center to feed and grow its black hole? The answer rewrites the story of cosmic evolution. If black holes led the dance, then their powerful influence was the primary architect of galactic structure from the start. Their intense radiation and colossal jets could have regulated star formation across the entire galaxy, heating gas or blowing it away to prevent new stars from forming too quickly. In this scenario, the black hole is not a passive passenger. It is the master of its domain, actively controlling the growth of its own home. But if galaxies formed first, then the black hole is more of a consequence, a byproduct of the chaotic processes of galaxy assembly. Gas flows and stellar collisions in the crowded galactic center could have naturally fed material into the middle, building up the black hole over time. Here, the galaxy sets the table, and the black hole simply eats what it is given. The truth may be a messy, intertwined feedback loop where both processes happen simultaneously, each fueling and limiting the other in a delicate cosmic balance. Unraveling this initial sequence is one of the primary goals of the James Webb Space Telescope. By looking at the very youngest galaxies, we can see if this mass correlation holds when the universe was in its infancy. If we find baby galaxies that are already too massive for their central black holes, or vice versa, it will tell us which partner took the lead in this ancient gravitational tango. The fate of a galaxy and the destiny of its black hole are inextricably linked, and the origin of that bond remains one of the most compelling mysteries of the dawn. Just as the cosmic fog was clearing, a second, more subtle transformation began. This is the epoch of helium reionization, a later and far less understood chapter in the universe's story. We often focus on the reionization of hydrogen, but the cosmos contains another primordial element, helium, which requires an even more powerful touch to change its nature. While hydrogen could be ionized by the fierce ultraviolet light from massive stars, helium holds onto its electrons more tightly. To strip them away requires photons of much higher energy deep in the extreme ultraviolet range. This points the investigation toward a new class of suspect. The likely culprits for this second wave of ionization were not stars, but the brilliant quasars powered by supermassive black holes. Only these cosmic engines, with their unimaginable gravitational power, could produce radiation fierce enough to rip electrons from helium atoms. This second reionization was a slower, more drawn-out process, a cosmic aftershock that heated the intergalactic medium to even higher temperatures. Think of the universe as a vast pot of water. Hydrogen reionization brought it to a simmer, but helium reionization turned up the heat, bringing it to a rolling boil. This additional heat had profound consequences. It made it more difficult for gas to cool and collapse into new galaxies, potentially putting a brake on star formation in the later stages of the cosmic dawn. This second wave of ionization adds a crucial layer of complexity to our narrative. It tells us that the clearing of the universe was not a single event, but a multi-stage process with different actors taking the lead at different times. First, the stars handled the hydrogen, then the black holes stepped in to finish the job on the helium, each phase leaving its own unique mark on the thermal history of the cosmos and shaping the future of galactic evolution in ways we are only beginning to comprehend. This cosmic feeding frenzy inevitably leads to a question of ultimate survival. What was the fate of the very first galaxies, the tiny, fragile islands of stars that first pierced the universal dark? The early cosmos was a dangerous place, a savage arena governed by gravity's relentless pull. Theory suggests that most of these primordial mini-galaxies were likely consumed, shredded, and digested by larger, more massive galaxies in a process of hierarchical growth. It was a cosmic game of survival of the fittest, where only the strongest gravitational structures endured. Our own Milky Way is a testament to this violent history, a galactic cannibal built from the devoured remains of countless smaller systems. Yet, could any of those first-generation galaxies have escaped this brutal fate? The thrilling possibility is that some pristine relics might still be lurking, virtually unchanged in our own cosmic backyard. Astronomers are now conducting an exhaustive hunt within our local group of galaxies, searching for the most ancient and faintest of all stellar systems, the ultra-faint dwarf galaxies. These are not the brilliant spirals or ellipticals we often picture. They are ghostly collections of a few thousand ancient stars, barely held together by gravity, emitting a faint light that is easily lost in the glare of their giant neighbors. Finding one of these cosmic fossils is the ultimate goal. It would be the astronomical equivalent of discovering a living dinosaur from the Jurassic era, a pristine window into the conditions of the cosmic dawn. But confirming such a discovery is incredibly difficult. How can we be sure a faint smudge of light is truly a first-generation building block and not just a torn-off piece of a larger galaxy? The evidence is written in the stars themselves and their motions. A true relic would show a very specific chemical signature, its stars containing almost nothing but hydrogen and helium, with only the faintest traces of heavier elements forged in those first supernovae. Its stars would all be extremely old, and the entire system would be dynamically pristine, not showing the gravitational scars of a past encounter or merger. Each candidate ultra-faint dwarf we find is put through this rigorous forensic examination. Those that pass become our most valuable time capsules. They allow us to study the properties of the smallest dark matter halos that ever managed to form stars, giving us direct insight into the very first steps of cosmic structure. The survival of even a handful of these fossils tells a story not just of creation, but of a quiet, lonely endurance across billions of years, a faint echo from the universe's first breath of light. Our entire view of the early universe might be built on a cosmic illusion. This is the subtle but profound challenge of cosmic variance. We are cosmic cartographers trying to map the entire Earth, but we are confined to a single city park. Our most powerful telescopes, like James Webb, peer into the deep sky by staring at tiny, specific patches of darkness for days on end. These deep fields are our windows to the dawn of time, but they are just that, windows, not panoramic views. The fundamental question is whether the view from our window is typical of the entire early cosmos. What if we have been staring at a rare cosmic metropolis? The stunningly bright and massive galaxies Webb found at the edge of time could be the norm, or they could be the equivalent of stumbling upon New York City while surveying what we thought was an empty continent. The rest of the universe at that time might be far emptier and darker, filled only with the faint, expected infant galaxies. This sampling error is not a mistake in our instruments, it is a fundamental limit of our perspective. The universe is simply too vast and our most powerful views too narrow to be certain we are seeing a fair representation. This uncertainty casts a shadow over every dramatic discovery. Are we rewriting the laws of physics, or have we just gotten incredibly lucky, or perhaps unlucky, with our first glimpse? The only way to know is to open more windows, to point our telescopes at many different, random patches of sky and count what we see. If every new deep field shows the same surprising abundance of brilliant early galaxies, then we know our models are truly broken. But if some fields are crowded and others are quiet, we will have to accept a more complex and varied beginning for our universe, one where the story of the cosmic dawn played out differently in different parts of the cosmos. The true nature of the beginning may not be a single, simple narrative, but a collection of local histories, and we are only just beginning to read the first page. These stellar nurseries were unlike any we see in our modern universe. The environment where the first stars were born was a place of pure, almost sterile simplicity, devoid of the cosmic dust and heavy elements that act as crucial cooling agents today. Without these ingredients, the very physics of star formation was fundamentally different. In present-day gas clouds, dust grains and molecules like carbon monoxide radiate heat away efficiently, allowing the cloud to fragment into many small, dense cores that collapse into stars of all sizes, from red dwarfs to blue giants. But in the primordial clouds, the only way for the gas to cool was through the faint emission of molecular hydrogen, a far less efficient process. This meant the gas could not shed its heat and fragment easily. Instead, these vast clouds of hydrogen and helium likely collapsed in on themselves as single, massive units, resisting the tendency to splinter into smaller pieces. The result would have been a stellar nursery of staggering scale and density, birthing not a spread of suns but a monolithic cluster of cosmic titans. This is the concept of a top-heavy initial mass function, where the first clusters were overwhelmingly dominated by stars hundreds of times more massive than our Sun. Isolated star formation was probably rare. The sheer mass of gas required to trigger collapse almost certainly meant that the first stars were born in crowded, frenetic families, shining with a collective ferocity that would outshine the brightest modern globular clusters. These clusters were the true powerhouses of the cosmic dawn, their collective ultraviolet radiation flooding the cosmos and their simultaneous supernova deaths seeding vast regions of space with the first heavy elements in a single, coordinated cataclysm. Unlocking the nature of these first nurseries is not just about understanding the first stars themselves. It is the key to the entire star formation history of the universe, for the violent lives and deaths of these clustered giants set the initial conditions for everything that followed, polluting the cosmos and forever changing how future generations of stars would be born. Buried deep within the faint radio whisper of the cosmos is a signal that could become the ultimate time machine. This is the 21-centimeter line, a specific radio frequency emitted by neutral hydrogen atoms as their electrons gently flip their spin. It is a universal constant, a quiet hum that has filled the universe since the beginning. During the Dark Ages and the cosmic dawn, this hum was everywhere, a perfect tracer of the hydrogen fog before any stars existed. As the universe expands, this light is stretched or redshifted to much longer wavelengths. By tuning our radio telescopes to different frequencies, we can effectively slice the early universe into thin chronological layers. Detecting this redshifted signal would gift us with a three-dimensional movie of the cosmos in its infancy, a tomographic map showing the distribution of all matter before the first star ever ignited. We could watch in real time as the first gravitational wells of dark matter began to pull the hydrogen gas into the cosmic web, and then witness the dramatic moment when the first brilliant bubbles of ionizing radiation began to pop and expand, burning away the neutral fog during reionization. This is the grand prize of modern cosmology. The challenge, however, is almost beyond comprehension. The signal we are trying to detect is incredibly faint, millions of times weaker than the radio glare from our own galaxy and the countless other sources that pollute our modern skies. It is like trying to hear a single snowflake land in the middle of a rock concert. To even attempt this, scientists are building vast radio telescope arrays in some of the most remote and radio-quiet places on Earth, like the deserts of South Africa and the outback of Western Australia. These instruments, such as the Hydrogen Epoch of Reionization Array and the Future Square Kilometer Array, are technological marvels designed to listen for this one specific cosmic note. Their success hinges on our ability to create unbelievably complex computer models to subtract the overwhelming foreground noise, a painstaking process of digital cleaning to reveal the pristine signal beneath. If we can finally pull this signal from the noise, it will not just confirm our theories. It will transform our understanding of the cosmic dawn from a collection of fragmentary clues into a complete dynamic story, allowing us to watch the universe wake up. Hidden within the brilliant depths of the first stars lies a quieter, more subtle creation story. Long after the light of a supernova fades, something tangible remains, the microscopic seeds of future worlds. Cosmic dust seems humble, mere specks of silicon, carbon, and iron smaller than a grain of sand, but in the economy of the cosmos, this dust is priceless. It acts as a universal coolant. Dust grains radiate heat away with incredible efficiency, allowing massive clouds of gas to shed their energy, collapse, and fragment into countless new stars. Without dust, the universe would be a far less productive place, unable to build the rich tapestry of galaxies we see today. This presents a profound chicken and egg problem. The first stars were born in a dust-free universe, yet to make the next generation of smaller, longer-lived stars, dust was essential. So where did the very first dust grains come from? The prime suspects are the same cataclysms that forged the first heavy elements, the supernova explosions of the population three giants. In the furious aftermath of such an explosion, as the expanding blast wave cools, newly forged atoms like carbon, oxygen, and silicon can collide and cling together in the chaotic void, nucleating the first solid particles in existence. It is a cosmic alchemy, transforming the pure energy of a stellar death into the physical grit that will one day form planets and people. The evidence for this early dust is etched into the light of the most distant quasars. When astronomers analyze this ancient light, they find it is not just absorbed by gas, it is also reddened, as if the quasar is seen through a faint cosmic haze. This reddening is the telltale signature of dust grains scattering the shorter, bluer wavelengths of light. The staggering implication is that significant amounts of dust already existed when the universe was less than 1 billion years old. This pushes the timeline for dust formation back into the era of the very first stars and their immediate descendants. Those titanic supernovae did not just pollute the cosmos with elements, they seeded it with the physical infrastructure for all future star formation, sprinkling the ashes of the first stars into the cradles of the next. Our final mystery brings us full circle back to the stellar titans that started it all. The ultimate fate of those first population 3 stars is not a single, simple story. Their deaths were as varied and dramatic as their lives, and their endings dictated the future of the cosmos. The most massive among them, those between about 150 and 250 times the mass of our Sun, likely met their end in the total annihilation of a pair instability supernova. But what about those that were even larger? For true behemoths above 250 solar masses, gravity's pull would have been utterly irresistible. Their cores, overwhelmed by their own weight, could have collapsed directly into a black hole without any supernova explosion at all. It would have been a silent, dark death. The star would have simply winked out of existence, leaving behind a voracious gravitational pit, a seed for the future supermassive giants we find at the centers of galaxies. This leads to a haunting and beautiful possibility. What if not all population 3 stars were giants? Our models suggest that a tiny fraction of them could have formed with much lower masses, perhaps only a few tens of times the mass of our Sun. These smaller first stars would have had vastly longer lifespans, burning their fuel not for a few million years, but for billions. Is it conceivable that a few of these ancient, slow-burning relics are still shining today, hiding in the halo of our own Milky Way? Finding one would be the discovery of the century, a living fossil from the dawn of time. The hunt is on, with astronomers meticulously scanning the skies for a star with a chemical composition of almost pure hydrogen and helium, a silent, ancient witness to the universe's first breath of light. The legacy of these first stars is all around us. Their explosive deaths forged the carbon in our bones, the oxygen we breathe, and the iron in our blood. Their silent collapses planted the seeds for the black holes that would one day anchor entire galaxies. They were the architects of the elemental universe, and their final, fading echoes set the stage for everything we are and everything we see. From the birth of the first stars to the silent echoes of gravitational waves, these 25 mysteries are not isolated puzzles. They are threads in a single, grand tapestry. The story of how a dark, empty universe transformed itself into a cosmos filled with light, structure, and the potential for life. The hunt for population 3 stars is linked to the riddle of helium reionization. The crisis of impossibly early galaxies is tied to the nature of dark matter itself. Every question we have explored is a single piece of a much larger picture, a picture we are only just beginning to assemble. We are living in a truly privileged moment, a golden age of cosmic discovery. For the first time in human history, we possess the tools to reach back and touch that dawn. The James Webb Space Telescope is not just a camera, it is a time machine, peeling back the layers of time to bring us face to face with the first galaxies. Giant radio arrays are listening for the faintest whisper from the neutral hydrogen that once filled the void. Each new observation, each new data point, is another piece of the puzzle falling into place, challenging our assumptions and forcing us to think bigger. This story is still being written, and you have a front row seat. Stay curious. Follow the latest revelations as they come in from observatories around the world and in space. Talk about these mysteries, ponder them, and share the wonder. Remember that the quest to understand our cosmic origins is a fundamental human journey. The next great breakthrough, the one that finally solves one of these enduring enigmas, will not just come from a telescope. It will come from a new idea, a fresh perspective, a spark of insight that could one day very well come from you.